Hello, this is my entry to the WTF contest. It's a monoplane, but it has a number of unique features that I'll demonstrate in just a minute. The most important features about this airplane is that there are no rudder controls, control surfaces or servos. There's no elevator control or surfaces. And there are no ailerons on the wings, and there are no flaps. So this airplane is minus most of the control surfaces that sometimes get into trouble, and sometimes are difficult to build. However, this airplane does have the ability to roll and pitch by the use of the wings themselves. And let me just do a quick demonstration. This is how we get the roll of the airplane. We actually twist the wings, and the pitch control is by shifting the wings together. So this is up and down, and that's a left turn. I'm sorry, a right turn, and there's a left turn. And there's up and down, or we can mix them. This is an old idea. It's been around for more than 20 years. And in the RC glider community. And this airplane is called a Pitcheron because it can tilt, or it can roll, and it can, use the up and down pitch of the wing to cause the plane to pitch up and down. Here's a little close-up to what's going on. And the mechanisms are inside here. I don't know if the light's going to be good enough to see it. But there are basically two servos that are inside the plane that can tilt either one of the wings, either together or opposite each other. So again, that's for turning, and this is for up, and that's for down. You still need a tail for those surfaces that force to interact and force the plane to pitch and roll. But that's, anyway, so this is a Pitcheron. The most unique feature about this airplane is there are no external control surfaces. Now, the other thing that's unique about this plane is it's sort of a engineering platform, as well as to work out some of the details and the bugs associated with Pitcherons, which I'll get to later on. But I wanted to disassemble very rapidly and also be able to get to the inside. So the disassembly process is rapid because all of the external parts are held in with magnets. And let me demonstrate. I'll disassemble the plane. The tail comes off. The wings come off. And there's the power control module. But I wanted to get into the guts of the airplane very rapidly. So not only does it come apart quickly because everything is held together with magnets, the insides of the airplane are on a drawer so that we can get very quickly to the components. And so this is the entire plane, all the mechanisms and wiring, and there are two servos here and here. This is a battery alarm, a radio, battery, and power section. So it's a very simple, easy to get to. Let me just pull the battery out so you can see it a little better. Idea. So the entire engineering of this was done with the concept of being able to remove all of the active components and get to them quickly. Have rather big hands, and so using the standard folded tube fuselage was sort of difficult to get in and do my engineering work. So this is obviously the main block that's got a 10 millimeter carbon fiber rod on the inside, and the wing support rod basically slides into there, these are spacers to keep the wings off of the side of the folded tube so that it doesn't rub. Let's look at the wing for a second. So the wing is a 7-inch wing, and it's just folded back and obviously and glued down, and there's no control surfaces. Again, there's a 10 millimeter carbon tube inside of here, and there's this control rod that sticks out. So in the plane, in operation, the wing twists on the 8 millimeter rod that's inserted inside the 10 millimeter rod, and the servos are connected to this rod, and that's what makes the wing go up and down. So it's very simple design. Very simple design on the wheels as well, and it allows me to get into the plane in 10 seconds and make engineering changes so that I can finally get the bugs out of the way that the wings tilt, and also the proper placement for a few items associated with the wing. So again, there's the work center drawer. That's one of the features. The quick disassembly is another feature. The Pitcheron idea is another feature, and almost as importantly is the use of a particular type of grease on the 8 millimeter rod, which goes into the wing. If you don't have a proper amount of damping when it's flying through the air, the wing can wander up and down if this carbon tube is located exactly in the center of the lift vector. So what I did was I offset it a little bit so that the wing lift vector is actually over here somewhere. So it puts a small amount of force on the servo under all operations, and that's sort of the key to making a happy Pitcheron airplane. Otherwise, if it was exactly centered on the lift vector, the wing would do a little bit of hunting. So we're going to take it outside and give it a try. All right, here's a walk around, last walk around before we fly the thing. Again, it's 63-inch wingspan, and it's 50 inches from spinner to tail. And we'll do one more test of the the Pitcheron, and looks like it's going pretty good. I think in this lighting you might be able to see the mechanism a little better. For the contest, and is it going to work or it's not? Nothing.
Oh, poop.
All right, here goes nothing. Ready? here we go. Well, I hope you enjoyed the video, and that is the end of the video. The rest of this is a slideshow, and I'm going to speak a little bit about components in the Pitcheron. This is the main block that holds the sliding tubes that tilt the wing. It's a bunch of 1/2-inch foam board cut up into pieces with 2 pieces of plywood, and obviously just sandwiched them together with Gorilla Glue. And after it's set, there was, I sanded it down, made it smooth, and this is what it looks like when it's finished. I cut the groove out on the top so we can get some airflow through the fuselage, and a little cutout on the bottom is for the wiring that goes back to the 2 servos. Let the paper on. Now there's an end view that's a 10mm outside diameter, 8mm inside diameter carbon tube. And it turns out that the tubes I bought, that with the 8mm fit nicely in it. And so this assembly is on a 1/2-inch board, of 1/2-inch foam board. I got an office supply place, and I made it sort of stiff in the back. That's 1/8-inch plywood, and in the front to the right was for the motor mount. This is aligning the tubes, the block to the foam board. And so I shimmed the 2 ends of the rod exactly the same and put Gorilla Glue, and then I'll let the Gorilla Glue, there you can see the shim right there. Gorilla Glue sort of added the precision that we needed. It glued with those rods lined up the way I had them shimmed. And let's see what the next slide is here. Oh yeah, so to get the folded fuselage to fit perfectly on the assembly, I made a few practice pieces. It was a couple inches wide. Ended up making 3 or 4 of them until I had just the right shape to go on there. And it slid on. It's, you know, they still had about 1/8 of an inch of clearance all the way around, which was just fine. It doesn't have to be absolutely perfect. Obviously, we would poke holes in the folded tube for the rod to go through. There's that finished assembly sitting on the folded tube, and I always use the Gorilla Glue to kind of give you a reference point for how big things are. This is a picture of the rod that goes through the block, and the 2 wings is up on the top. That's 8mm, and the 2 bars or rods on the bottom of the 2 rods that go inside the wing. Those are 10mm outside diameter rods. There's a picture that shows the 10mm rod, and if it were in the wing, sliding onto the 8mm rod, which is in the block. The block, of course, is another 10mm rod. That's the spar for the wing. It's a 7-inch wing with no control surfaces, and the top is of the wing is where the 10mm carbon rod is. And it's just an end view right there. And the foam board folded over very nicely. I rounded off the edges, those top 2 corners on the left and right, and folded over real nice. This is inside the wing. That's the spar. That's a little piece of metal that's at the end of the 10mm shaft that's in the wing, and that's what the magnet is going to stick to. I put magnets on the inside of the wing. There's 5 little tiny samarium cobalt magnets attached to the metal,
and the rod, of course, goes in. The 8mm rod goes inside of it, and it has a magnet on the inside of it. And this is the gluing up of the wing section so that the spar would be aligned to each wing. You know, Experimental Airlines explains this technique very well. This is where I tried to cut their 8mm rod perfectly. So I put the two wings together with the rod too long. I kept cutting a little shim, that little piece of white paper or foam, until it fit perfect. I measured it, and then I used that dimension to cut the rod to the exact length. The rods need to touch those two pieces of metal that are glued at the end of the 10mm rods. And so then I put magnets up inside the 8mm rod, which you don't see them, but they're inside that rod. But first I put hot glue in there, then I pushed the magnets up in there, and then I pushed down against a piece of wax paper. And there you see that's dried now, and you can see through the wax paper, you can see the samarium cobalt magnet right at the end of the tube where it needs to be. It has to be sticking out ever so slightly, or at least flush with it. It should be flush. So then you take and grind down the tube, make a cone so that the magnet is the only surface that's sticking out. So we'll make a metal to metal touch of that metal plate that's on the end of the 10mm rod that's in the wing. This is where I shimmed the two ends of the 8mm rod on left and right, and so I could keep those absolutely perfect while I glued on the tail assembly. Here's an example of the control rods that stick out of the wing. They slide in those grooves. Those are the synchro arms that I put small grooves in, so they'll slide back and forth. You can see in this next assembly how they're mounted. Now we're looking at them vertically, and the two shiny pins that are fitting in those grooves. As the servos rotate, those pins need to slide in that groove. And there's a better picture right there. If you can imagine an arm going up and down, how necessary it is for that rod to slide in that groove. I polished them with Brasso so that they would not chew up the plastic arms. And there's the outside skin again, and the hole in it for the rod, the wing axle rod, and the groove for those shiny pins. And obviously I put the wheel assembly there. That's the stack up for the at the motor end, and you can see there's 1/2-inch foam board there, there's 1/8-inch plywood, and the rest of it is the standard Dollar Tree foam board. And yes, that was a GoPro taped to a cowboy hat, I have to admit. But wait, there's more. What self-respecting experimenter wouldn't show the bad with the good, especially with a new plane design like this? And what RC video wouldn't be complete without a straight down 60-mile-an-hour nosedive like this?
Oh, Jesus.
The reason for the crash was recorded on the tail camera, which actually ended up being a flight data recorder. And this is the video of that crash. You can see how the wings are responding. The airplane is responding to the wing position, and they're moving around pretty easily. What I found out was that in a nosedive, the wind force against the wings bent the 8mm and 10mm carbon rods sufficiently that they built up friction and basically jammed. And at the end of the video, when it goes into the tail dive, the friction buildup inside those axles are so severe that the little servos couldn't force them to move. And then if you stop this frame by frame towards the end, you'll see that the right wing is jammed solid, and the right servo arm is pushing against it and actually bent in such a way that it's actually at about a 20-degree, 30-degree angle. You can see it right there. If you back up the film.
Okay, this is the postmortem on the airplane. The wings are in fantastic shape. Even though they hit the ground pretty hard, there's a small bruise in this wing and a little crinkle, but it's still very strong. So this is good for another day. And this wing is basically untouched. The 1/2-inch foam board acted as a crumple zone to absorb all the energy of the crash. I don't know if the motor survived or not. We'll figure that out. But most importantly, this crunch zone allowed for the entire mechanism to stay in one piece, even though the 8mm rod snapped off on one of the wings. So this is good for another day. All I got to do is cut this foam board off and put a new piece on, and we can go try it again. The next iteration, I'm pretty sure the reason that the airplane failed was because of this long 8mm tube inside this wing, and basically the 8mm and 10mm rod, when they bent, the clearance went to 0 and the friction was too high for the servos to move. So on the next iteration, I'm going to use a very short shaft, and I think a few inches, maybe 6 inches is plenty. That way it won't bend so far that it will distort, and the magnets are too far in for those to work on this particular plane. But instead of using magnets, you can put these little wall hooks on the plane that stick on and use a rubber band. And you can see that this rubber band is not quite strong enough, but you can see that basically the rubber band should be able to hold the wings in place. And if you do it at the pivot point, they won't put any stress on the servo. So that's my next plan, and I'll make a video when we get it going. Thanks for watching.